Hello, everyone. So I've been asked to go through chapter 11.5 of the Hyman textbook, which is on reaction pathways. So we're going to discuss what's in 11.5, but also what's in the preceding two chapters, just because they closely link into each other there. So if you take a look at the key knowledge for these chapters, most of it is in 11.3 and 11.4. We've got all of these different reactions, which hopefully you've had a look at. I'm going to go through and kind of summarize them very quickly. But basically all of them, because we're not going into reaction mechanisms, i.e. How the reactions actually happen, it basically just comes down to you need to know if you have this thing and you add this thing, what does it make? Or if you have this thing and want to get to this, what do we add in the middle? So that's all of this stuff here. Now 11.5 is this one here, which is the pathways used. Now, this is actually kind of hard to say exactly what this is without looking at what VCAA stuck into the exams. So we're just going to take a look at a bunch of basically all of the exam questions that VCAA's put on the official exams for the last few years. And you'll see what kind of things that they kind of mean here. If you know everything from 11.3 and 11.4, you can probably figure out what is in 11.5 logically rather than actually needing to go and read about it. But we'll go over exactly how we're applying those reactions that we learn in 11.3 and 4 into 11.5. All right. So to start up with, I've got a giant list of reactions here. Basically, you should have covered each of these. But basically, we're going to know a bunch of different reactions from chapter 11. I'll go through them in a second. And basically, you just need to know, them all and what happens if you combine two things. So, and what to do if you want a certain one. So for example, if you want a haloalkane, what would you do to get there? Okay, well, if you have an alkene and you want to get to a haloalkane, we could add a hydrogen halide, so hydrogen chloride or something like that. So just to go through them quickly in order, we've got combustion, which is kind of its own thing. Now I've listed it up here for completeness and because it's basically the one consistent reaction between organic compounds, but you're not really going to see this come up in a reaction pathway because if you burn something, you can't do anything with it anymore. If you get carbon dioxide, but normally either it's easier to just get carbon dioxide from somewhere else, so you wouldn't do it in a synthesis reaction anyway because it's more expensive to buy the organic compound than it is to buy carbon dioxide, and the carbon dioxide will float off, so you have to have some kind of gas container to keep it anyway. Basically, this is what we do with fuels if we want to get that heat release, but if we're doing a reaction, which is most of unit 4, we don't really want to do combustion. All right. So I've ordered these in terms of what reactions we can do from a starting compound. So to start off with, if we have an alkane, basically the only reactions that we can do combustion, of course, and we can also do substitution reactions. So here we've got an alkane, we add a halogen, and in the presence of UV light, so normally you would write this above the arrow, but it will be a bit too small to read there. You can put like a little UV over there is how it's normally written. A little UV over the top there. An alkane plus a halogen in the presence of UV light will give us a haloalkane. Now, for the sake of year 12, this is literally the only thing that an alkane can do. So if you see an alkane in a reaction pathway, you know that it is going to turn into a haloalkane. And then you can do something with the haloalkane. These guys are much more reactive than alkanes. So basically, if you actually want to turn your alkane into anything more useful, you're going to have to go via some kind of chloroalkane or fluoroalkane or something like that. The haloalkanes themselves, we've got two main reactions here. Basically, we have another kind of substitution reaction where we're replacing the halogen on the haloalkane with something else. So we're taking, say, chloropropane here, and basically if we add hydroxide, the hydroxide will come in and bump the chloride off, and it'll just replace it. So in our alkane substitution, we were replacing a hydrogen with a halide. Here we're replacing a halide with a hydroxide or an ammonia. So this is how we get an alcohol. So already you should be able to see the kind of reaction pathway that we can get here. So we go from an alkane to a haloalkane to an alcohol. So if you started with propane and you wanted to get propanol, you would have to do 2 steps there. You can't just go, oh, I'll just add hydroxide to propane. That doesn't work. We need to go via that intermediate. We can also add ammonia instead of hydroxide, and we'll end up with an amine. So we would end up with this guy here. All right, the alkenes have a bunch of different things that they can turn into, which we talked a little bit before, and they're all going to be addition reactions. So we're basically assuming that the only thing the alkenes do is addition. So we get a small molecule and it's going to split in half and add across it. So an alkene, basically we add a hydrogen halide, we get haloalkane. Add hydrogen, we can get an alkane. This one's not super useful because you don't normally try and make alkanes. Like if you want an alkane, you can just pull it out of crude oil. So we don't tend to use this one a lot. This one, you need to use a nickel catalyst as well. Use a halogen gas, you get a dihaloalkane. And the main one that this one is kind of come up more often for the sake of this year. You can add water to make an alcohol. Now we need phosphoric acid, remember H3PO4, and about 300 degrees Celsius as well. We can also add alkenes together to make polymers. We don't really discuss polymers in year 12, but it's a thing that they can do as well. So the main ones here are, you can add a hydrogen halide to get a haloalkane, and you can add water to get an alcohol. You do need to know these ones as well, but the main ones that will come up in a reaction pathway are making the alcohol and the haloalkane. All right, so they're all the ones on alkanes and alkenes. Alcohols, the main one that they can do is that they can turn into a carboxylic acid via an aldehyde here. So this reaction basically, depending on how vigorously you do the reaction, you can get it to stop at the aldehyde or you can get it to stop at the carboxylic acid. Now, the curriculum doesn't say you need to be able to do reaction pathways to make an aldehyde, so it's not going to pop up in a standard reaction after reaction after reaction type thing. It's basically just if you smash it with acid and dichromate being Cr2O7, you're going to go straight from the primary alcohol to the carboxylic acid. Note that this only works with the primary alcohol. So if you want to make a carboxylic acid, you're going to need to use a primary alcohol. If you instead use a secondary alcohol, it'll turn into a ketone. Now again, ketones don't show up in the curriculum. So you need to be aware of that this reaction exists, but it won't show up in a pathway. All right. So this really, if you've got an alcohol and it turns into something else in a pathway, because it's the only one we're talking about, it's basically guaranteed that your primary alcohol is going to turn into a carboxylic acid. It'll go straight from the alcohol to the acid there. All right. Once we've got carboxylic acids, there's basically 2 things they can do. Either we combine them with an alcohol and they're going to turn into an ester and release water in the process. This needs acid. Or we'd add an amine and we end up with an amide and water again. And the reaction of carboxylic acids with alcohols, i.e. esterification reactions, are reversible. So you can go from the carboxylic acid to the alcohol and it'll make an ester. It'll also go backwards and can turn the ester back into carboxylic acid and alcohol. So again, useful thing to point out here, the ester can only ever turn into a carboxylic acid and alcohol. That's the only thing they're ever going to do in a reaction. It's very common for questions, for VCAA questions, to have an ester as the last thing, just because they're a common thing to make synthetically. So they're useful in terms of flavoring and having nice smells and things like that. So we like making them. And they're useful in drugs and things like that. It's a relatively easy synthesis. So we tend to make an ester as opposed to break it apart, but this is something that can potentially show up. So they're the reactions. In terms of if you need to name them, you can basically count on alkanes and haloalkanes always undergoing substitution reactions. That's the only one they do. Alkanes are always going to do addition reactions. alcohols can undergo oxidation or esterification. So oxidation, if they've got some kind of metal oxidant in there, so normally dichromate, or esterification if there's a carboxylic acid in there. Carboxylic acid always going to undergo an esterification or an amidation reaction, so becoming an amide. And esters and amides are always going to undergo hydrolysis reactions. That's the only one we've covered this year, so it's the only possible one to show up. I have ignored combustion reactions for the sake of these, again, because it's not really a synthetic reaction. It's more of a decomposition reaction. All right, so let's have a look at some of the VCAA questions. I basically pulled out all of the pathways questions from the last 5 years. They all look really similar. They're all basically these ones where you've got a bunch of chemicals, either names or formulae in a row, and they say just fill in the boxes. That's all that it's really asking you to do in terms of the reaction pathways. So we've got hex 3-ene here. So let me draw a skeletal formula for that. 1, 2, 3, 4, 5. I need one more. 1, 2, 3, and it's got a double bond here. All right, so we got a double bond in the middle. One thing to note about this is that it is symmetrical, which is going to be relevant in a second. So basically, all of the questions underneath this in the VCAA handbook, in the VCAA exam, are just saying fill in this box, fill in this box, fill in this box, etc. So let's have a look at this. Hex 3-ene. If we add hydrogen bromide, we know that it's an alkene, so it's always going to undergo an addition reaction. Now, normally when you've got something like this, it'll make two different isomers, because just will the bromine add here, or the bromine add here? Because this particular one's symmetrical, there's only one thing it can make. It's going to be like that, the bromine here, and then continue on. You can imagine that if the bromine was here instead, it would still be the same thing. This is 3-bromohexane. If the bromine's on the other side, it's also 3-bromohexane. So I'll put the name in there as well. All right. In the other one, we've got hexene going to hexane 3-ol. So remember, we know that it's going to be an addition reaction. The only way that it's going to get to an alcohol is if we add an OH to it. So we need to add water in this case here. So we're going to add water. And now it's also important to note that you need to add an acid here. Water isn't super reactive by itself. The acid is going to help to catalyze that reaction. Water's pretty slow at reacting with organic things. So we add the water and the phosphoric acid are the two reagents we need there. All right, let's go down to the right to compound K. So we've got hexane 3-ol, which is going to look like this. Oops. It's going to have 6 carbons, and then the OH on the third one there. And if we're adding permanganate down here, whenever you see some kind of metal, especially if it's in a high oxidation state, so for example, this manganese is in +7, which is why it's a really, really strong oxidant, it's going to oxidize whatever chemical we're looking at. And we know that if we've got an alcohol and we oxidize it, it's either going to become an aldehyde if it's primary, a carboxylic acid if it's primary via an aldehyde, or it's going to become a ketone. So for the sake of this one here, it's going to go from an alcohol to a ketone. Now, apparently my pen has died, so I'm going to have to draw this quite poorly. So we're going to just keep going with what we already had. 1, 2, 3, 4, 5, 6. Now remember we had the OH here before. Instead of the OH, it's just going to be replaced with a carbon double bonded to an oxygen, like that. There you go. So it's going to look like that. You don't need to be able to name ketones, but incidentally, this would be called hexane 3-one. There we go, we're back. All right, we've got an alcohol here. It's being combined with another organic compound into something down here. Now, if you combine two organic compounds together, for the sake of year 12 again, it's basically always going to be an ester or an amide. We've got no nitrogens here, so even without looking at it, I know that it's going to be an ester. And sure enough, we see that there's this carbon double bonded to an oxygen and single bonded to another oxygen, so it's an ester. Now, what we've got here is we kind of got we're kind of in a position where we have something like this in maths, right? Like we know one of the things we start with and we know what we end with, so we have to figure out what's the difference between it. So we can look at our hexane 3ol. Let's draw that in comparison. 1, 2, 3, 4, 5, 6, like that. Okay. And what's the difference between this picture here and this picture here? Well, it's going to be whatever's over here. And we see over here, we've got 2 carbons. We know that we combine that it's always going to be carboxylic acid reacting with the alcohol. So whatever compound M is, it must be carboxylic acid, and it has 2 carbons. Now, there's only one option there, and it's ethanoic acid. So we can draw that. There you go. We've got acetic or ethanoic acid there, and it's being catalyzed by sulfuric acid. Incidentally, glacial acetic acid because it's liquid, not aqueous. And there you go. So that's going to be worth about 5 marks on the exam. All right, let's keep going. As I said, most of these questions look pretty similar. It's a bunch of boxes with a bunch of arrows going between them. This one's got kind of the questions written directly into it, so it's not like reliant on stuff being written underneath it. But let's go from the top. So you've got pent-2-ene. We want a skeletal formula. So it's 1, 2, 3, 4, 5. And the double bond's going to be between the second and the third carbon. So there you go. There's a mark right there. We add water to it in the presence of acid, and we get 2 things out. So they must be isomers because they were getting the same product out from the single reaction. And that's because when we have our double bond here, there's 2 options. Either the OH attaches to the one on the left here, and we get this, or it attaches to the one on the right. And they're 2 different compounds. And now we get told this extra information because otherwise we wouldn't be able to answer it, that one of them contains a chiral carbon and one of them doesn't contain a chiral carbon. This is one of the few places that chirality has actually shown up. It tends to show up like 1 mark or so, 1 or 2 marks or so per exam. And they're often shown up in these ways that basically it's part of another question that you need to know, as opposed to just getting an explicit question that says, what is chirality? Or something like that. So here you need to know about chirality to answer this other question that's on synthetic pathways. So one of these has a chiral carbon, and one of these doesn't. This one's a little bit tricky, actually. And so let's have a look at the only possible chiral centers are the ones which have the OH on them, because everything else is just lots of hydrogens everywhere. So I'm going to add the other things, on the hydrogens onto here so we can have a look at it. This one at the top, we've got this one on the side here. It has a hydrogen, it has a hydroxyl, it has a methyl, and it has a propyl group. So that's 4 different groups going around it. So this is going to be a chiral compound. So we can go ahead and say that this one must be this one here. This one here it looks pretty chiral to start off with. It has a hydrogen, it has a hydroxyl, it has an ethyl, and it has another ethyl. It's because it's symmetrical around that hydroxyl group. It means that it's not, it doesn't have the stereoisomers. So compound M, which is this, is going to be pentane 2-ol. And the non-chiral one would be this. And we've got pentane 2-ol. So remember, we're looking at this. And it's going to be hit with some kind of metal compound. Again, dichromate. We've got a really high oxidation state for the chromium. It's about +6, I believe. And some acid. This is going to be an oxidation reaction. We've got a secondary alcohol here, so therefore it's going to become a ketone. So we're going to end up with this here, 2, 3, 4, 5. Yep, going to end up with that. And it says semi-structural formula. So going from left to right, I always like to draw out the skeletal formulas, even if I'm doing semi-structural, just so I don't mess it up. So CH3, CO, CH2, CH2, CH3. Semi-structural are assuming that whoever's reading it can go and figure out what the bonds are from the amount of hydrogens around. There we go. So another few marks from that question there. Let's keep going. This is one more of a written one here. This one's more along the lines of 11.3 and 11.4. But let's have a look at this. We've got 2-chloropropane. So that looks like this. can be reacted with ammonia to produce an uncharged organic molecule compound R. Write the equation for the reaction that occurs. So let's just have a think about what the reaction is. First, I'm going to draw it skeletally because it's easy to think about. 2-chloropropane, it's reacting with ammonia. What's the only type of reaction that a haloalkane can undergo? It's going to be a substitution reaction. Again, for the sake of Year 12, all of these chemicals can do hundreds of reactions, but for the sake of Year 12, we're just going to say it's just doing substitution. So ammonia is going to come in, its electrons are going to attack here, and the chlorine will fall off, or the chloride will fall off. And we'll end up with the ammonia replacing the chloride, and the hydrogen will come off the ammonia and form hydrochloric acid here. So let's write that out just in terms of molecular formulas, so it's as easy as possible. 3 carbons, there's going to be 3, 6, 7 hydrogens, and a chlorine, plus ammonia goes to, it'll be the same thing, but just with an NH2 group instead of the chlorine, plus HCl. There you go. All right. Give the IUPAC name of compound R. We've made compound R, so this is going to be propane to amine. All right, and the type of reaction that produces compound R, it's going to be a substitution reaction. These are nice, easy marks for you to pick up that are going to give you more time to be working on the kind of harder ones. All right, let's keep going. So we've got compound M. We don't know what it is, so we're going to have to do what's called a retrosynthesis. So have a look at what our final product is and go, okay, how are we going to get to that? So let's just ignore this bottom bit for now. Oops, didn't want to cross out propanol. Let's just ignore this bit for now. And so, okay, we've got propan-1-ol as what we want to make. How would we get to propan-1-ol? Okay, well, we can add water to it. What do we add water to that will make propan-1-ol? It's going to have to be an alkene, isn't it? So if we've got an alkene, there's only one alkene that we can actually make from 3 carbons. So it's going to have to be propene like this. Now remember, there's no prop-1ene and prop-2ene, just because if you put the double bond on the other side, it's just still symmetrical. So this one is going to have to be this one here. And it does say semi-structural formula, so we're CH3. This one is just CH and CH2. There you go. That's semi-structural formula. Now let's keep looking at the next one. The next step. How do we get from a primary alcohol to a carboxylic acid? We're going to need to have oxidizing agents there, aren't we? So we're going to have that. And then if we go and have a look back here, when we're trying to get from a primary alcohol to a carboxylic acid, we're going to need some acid as well. So kind of put whatever we want as the acid there. Just write H+ is a pretty easy one to do. Just saying, put some kind of acid in there. All right, so we've got acetic acid here. Let's try and get that to rub out. There we go. So we've got acetic acid here. Sorry, no, we don't. We have propanoic acid here, and we're adding an amine and an acid. Now we know that the only thing that an amine and a carboxylic acid would ever do together is combine together and make an amide. So it can be, one thing that's easy to do is to draw them next to each other and to just kind of knock out a water from the middle. So this is what we've got, ignoring hydrogens, and these guys are all going to get deleted basically, and we're going to be left with whatever's left. So I'll rub those out. We don't have those anymore, and instead we just have a bond there. So going there, it's going to look like this. And going from left to right, we need semi-structural. CH3, CH2, CO, NH, CH2, CH3. And that's our amide. All right. Close to done. So complete this reaction at the top. We're going from ethene to ethanol. we know that it's always going to be an addition. So what do we need to do? We're adding 2 hydrogens and an oxygen. Hopefully by this stage you're like, oh, 2 hydrogens and oxygen, that sounds an awful lot like water. Indeed, water it is. The catalyst here would be the H+, so we don't need to add that as an extra reaction. The H+ does come back at the end of the reaction, so you wouldn't see a change in pH. All right, and then we're taking this ethanol, we're adding something to it to make it into acetic acid. So it's saying 1 reagent, so we're just going to put dichromate in there. It would be in the presence of an acid as well. All right, can be used in the production of esters. Write a balanced chemical equation for the reaction of acetic acid with propane 1-ol. So we're going to go ahead. It's going to be acetic acid plus propane 1-ol. It's going to be CH3, CH2, CH2OH. And it's going to make, so we know it's going to be like this. With the OH, carbon, carbon, carbon. There's a carbon there. These guys are all going to get deleted. And it's going to look like this. OCCC. So let's go through that. CH3, COO, CH2, CH2. Oops, not plus. CH3. And the other thing, we need to remember that this is a condensation reaction. We lose the water here, it doesn't disappear. We know that atoms don't randomly disappear. It's going to be a product. All right, so we've got that there. And write the IUPAC name for the ester product of the equation there. So we've got 3 there, so it's going to be propyl. Remember, the prefix thing here is going to be the one that's on the side of the single bonded oxygen. And then the base one here, which has the double bonded oxygen on it, is going to be either acetate, or because we're going for IUPAC, we'll write propyl ethanoate instead. There we go, 5 marks again. 5 marks? Yes. All right, and I think we're just about done. So for the last one, we've got but1ene. Now we've been asked for a structural formula. Remember, a structural formula has hydrogens on it. So I'm gonna start with my kind of skeletal formula, put my double bond on, and then just add all the hydrogens in at the end. 1, 2, 3. All right. And we're going to add something to that to make it into something else. Okay, that's not particularly helpful. Let's look for the end. Butanoic acid. Oh, okay, that's going to ask for a semi-structural formula, so we may as well just do that now as well. So CH3, CH2, CH2, COOH is our semi-structural formula. Now, what are reagents here? Remember, when we're seeing those high oxidation state metals, they're going to be oxidizing something. So what do we oxidize to get a carboxylic acid? It's going to be an alcohol. It's going to be an alcohol, primary alcohol with 4 carbons. So it's going to be butan 1-ol. All right. How do we get from but1ene to butan 1-ol? We're going to have to add water across it. So we're going to have to add H2O and H+. So we need to add H2O and H+ to get butan 1-ol. Incidentally, this would make one product. We could also, if you got asked what the other isomer would be, remember that the OH could add here, that would give the butan 1-ol. It could also add here, which would end up with a secondary alcohol here. And then that would end up, if you put the same conditions on it, you would end up with a ketone there. But that's not asked here, so you don't need it. All right. So hopefully that was a helpful look at 11.5. Please send me an email or leave a comment if you have a particular question about that. All right. Thanks for watching.